In this example, we have let w equal -1 minus I. We will find all complex fifth roots of w and represent your answer in complex polar form r/CIS of theta. That means that we are going to keep our answers in complex polar form. You do not need to change them into rectangular, but if you would like to do so to test your knowledge, by all means. Note that the question does say to find all complex fifth roots. Since we are taking this complex number to the 1/5 power, that means therefore that there are going to be 5 answers for this. The fifth root will have 5 solutions. However, before we can go and work with the root formula for complex numbers, we are going to need to first change w into complex polar form. Let's quickly do that. With w here, we need both the modulus and the argument. The modulus for w, this would be based on the Pythagorean theorem of -1 squared plus -1 squared, or just square root of 2. The argument for w, however, if we use arctangent, we do need to be aware where the original complex number is. -1 minus I on the complex polar plane would have negative real and negative imaginary. This angle measure should be down in quadrant 3. If I just work with arctangent of the imaginary value over the real value, this would actually result in an angle measure in quadrant 1, as -1 divided by -1 is +1. So if we need to adjust this angle measure, we should, and to get into quadrant 3, we will add pi to the solution. If you do evaluate arctangent of -1 over -1, or just arctangent of 1, that will give you pi over 4, but if you add pi to that, we get the correct angle measure in quadrant 3, which would be 5 pi over 4. Therefore, we can now write w as, in complex polar form, square root of 2 CIS of 5 pi over 4. Using this condensed form of the complex polar form, we can now apply the root formula in order to come up with the 5 complex fifth roots of w. So let's do that. If we're going to find the fifth roots of w, and we have 5 solutions, I'll represent those with subscripts. W to the 1/5 power, I'll use z with different subscripts. So I'll say z sub 0 is our first subscript we use, and I'll keep using subscripts until I have 5 solutions. There we go. Z sub 0 up to z sub 4, I have 1, 2, 3, 4, 5 answers from this. Those subscripts are going to be important, as those are the values that we're going to plug into k for the root theorem. Now, to demonstrate where all these are coming from, I'm actually going to color code this a little bit, so hopefully this will be a little bit more obvious. I'm going to color code the subscripts, and I'll choose a color of black for that. 0, 1, 2, 3, and 4. And I'm also going to color code the root, so you see where we apply this accordingly. So instead of 1/5, I'll color that in green, so 1/5. So, to do the first root, we're going to take the original modulus, square root of 2, and we're going to take that to the 1/5 power. Then, we'll multiply that by CIS of our angle measure, 5 pi over 4, and we're going to divide that by 5, based on the root that we're working with. We will then also have plus 2 pi, that will also be divided by the root that we were working with. And we're going to multiply 2 pi over 5 by our subscript of 0. This is the general format that all of our solutions are going to look like. So for example, the next solution will be square root of 2, again to the 1/5 power. times CIS of 5 pi over 4 divided by 5 yet again, plus 2 pi also divided by 5. But this will now be multiplied by the subscript of 1 that we have on Z. The other three solutions are all going to look the same, and I will quickly go through and generate those. I have now gone through and generated our 5 solutions that are all using the same format. The only thing that is changing from one root to the next is the value that I input for k. So let's simplify these into complex polar form. Square root of 2 to the 1/5 power. Well, the square root of 2 to the 1/5 you can consider as 2 to the 1/2 power, which is taken to the 1/5, and that means that we will multiply those powers to get 2 to the 1/10 power. So my answer here will be 2 to the 1/10, or the 10th root of 2 if you prefer, times CIS of 5 pi over 4 divided by 5 would just be pi over 4, plus this expression would equal 0, so that is it for my first solution. The second solution will be 2 to the 1/10 power, CIS of, again, it'll be pi fourths plus 2 pi fifths. Pi fourths plus 2 pi fifths. I can simplify that even further as 2 to the 1/10 CIS of pi fourths plus 2 pi fifths. That would be 5 pi 20ths plus 8 pi 20ths is 13 pi 20ths. Note that when I figured out what I'm going to be adding in terms of 20ths, that this is 8 pi 20ths, that means all my other answers are just going to be adding another instance of 8 pi 20ths, or 2 pi fifths. So I can start to more quickly generate my answers, because I know my next one will just be 13 pi 20ths plus another 8 pi 20ths. 13 plus 8 will give me 21 pi over 20. The next one then would be 2 to the 1/10. CIS of another 8 pi 20ths after that would be 29 pi over 20. And then plus another 8 pi 20ths after that. 29 plus 8 would give me 37 pi over 20. So we have our 5 answers. First one there. Second one here. The last 3 here. Quick note, if you were to do this one more time by adding another 8 pi 20ths to our last angle measure we got, what you would get is 45 pi over 20, which is actually an angle measure larger than 2 pi. And if you simplify that down by finding a coterminal angle measure to it, you will get 5 pi over 20, otherwise known as pi over 4, which was the first angle measure we had in our first solution. So adding another instance of 8 pi 20ths would just start to repeat the solutions that we've already developed. It's a nice way to check to see if you do already have all of your answers.